Okay, so we have seen circuits where the resistors are in parallel and we found the equivalent resistance. We also saw circuits where the resistors are in series and we found the equivalent resistance. Now what we are going to do is we are going to study circuits where instead of resistances we'll have capacitors. Okay, so here on this slide we have the two cases that we are going to study. On the top case, we have capacitors in parallel, right? We have here a battery, and then we split these lines into three. Each line has a different capacitor, okay? So we want to find what is the equivalent capacitance for this circuit. Here at the bottom, we have capacitors in series. You see that we have a single line, we have the battery here, and then a single line, and then we go one after the other, we put a capacitor, okay? And we want to find what is the equivalent capacitance for this circuit as well. Okay, so let's start by reminding ourselves what we saw in chapter 17 when we discussed capacitors. So capacitor is a device to store electric charge. And we saw that the charge of this capacitor, the charge that is stored in each plate of this capacitor is given by the capacitance of this capacitor and by the potential difference. So the battery will feed the charge to this capacitor. Okay, so let's keep this. This is going to be useful for our study. So let's start with the capacitors in parallel. All right, and what we want to obtain a circuit where I have a single capacitance, this C equivalent, a single capacitance that will draw from this battery the same Q, that we have in this equivalent in this circuit here, in this circuit in parallel. Okay, so we want to find what is this equivalent capacitor. Okay, so what do we have for this circuit in parallel? Very similar to what we talked about when we had resistors. What we have here is these capacitors will suck current out of the battery. So the current comes, we have the Q coming here, but then it splits. So the Q that was drawn from the battery will split. Q1 will go to capacitor C1, Q2 to the capacitor C2, Q3 to the capacitor C3. Now, so we have the split of current, very similar, the split of charge, very similar to what we had before for the resistors, where we had that split of current. Okay, so what do we know about this circuit in parallel where the capacitors are in parallel? That the Q splits in Q1 plus Q2 plus Q3. Okay, what else do we know in this circuit? What we know that each one of these capacitors are subjected to the same potential difference, the VA minus VB. Is VA minus VB for this one, is VA minus VB for this one, is VA minus VB for this one. VA minus VB is the potential difference of the battery. So we know that the potential difference is the same for all capacitors. Okay, with these two information, with this point here and this other point here, we will be able to obtain this equivalent capacitance. So let's start by using this equation that we just wrote. But let's use this equation in terms of the capacitance and the potential difference. So what is Q for this circuit, for this equivalent circuit here? Q is going to be equal to the equivalent capacitance that we are after multiplied by the potential difference of the battery. Okay, now let's go to the other side of the equation. What is Q1? Q1 is the capacitance of the capacitor C1, right? This one, multiplied by the potential difference of this capacitor, and the potential difference of this capacitor is again the potential difference of the battery because this circuit is in parallel. How about Q2? Well, Q2 is C2, the capacitance for our capacitor 2, multiplied by the potential difference, which is again V. And then finally, Q3, which is C3, capacitor for capacitor 3, multiplied by the potential difference. So the potential difference is the same everywhere, so I can get rid of this, and I find that the equivalent capacitance is now, careful, the sum of the capacitance. Okay, so this is interesting. Here we have that a circuit where the capacitors are in parallel, the equivalent capacitance is given by the sum. So careful with this, don't get confused when you're playing with resistances and when you're playing with the capacitance. Okay, the equivalent capacitance for a circuit in parallel is the sum of them. Okay, so it's the opposite of what we saw for the resistances. In the resistance in parallel, we had to play with those ratios. Now 1 over the equivalent resistance. Here is just the sum. Okay? All right. Why is that? Because, look, in the case of capacitors, we have the Q is CV. In the case of current, when we are talking about Ohm's law, what we had is that I is V over R. Okay, so that's what changes these equations. Okay, that's why in the case of resistances in parallel, we were playing with that 1 over the equivalent resistance. While here, since charge Q is CV, we have the sum of the capacitance. Anyway, the message is be careful not to confuse equivalent resistance with equivalent capacitance. Capacitors in parallel, the equivalent capacitance is the sum of them. All right? Okay, now let's move to the other case, which is when we have here at the bottom capacitors now in series. Capacitors in series, in a way similar to what we saw for the case of resistors. What did we say that? In the case of resistors, the current had to go through each one of these resistances. Okay. Now, in the case of the capacitors, what we have that the Q has to be the same. Because if there would be any little difference between these Qs, well, the electrons will move away. And so they want to find this equilibrium where he is minus Q and he is plus Q. He is minus Q and this is plus Q. All the same Q. Okay. So now it's similar to the case of resistances where the current that had to go through all of them was the same. Okay. So let's write this down. When we have capacitors in series, the Q is the same for all capacitors. Okay, so there is this balance. If there was not, the electrons would still be moving until they would find this balance. Okay, what else do we have? Well, we have that the potential difference of the battery now is given by the sum of the potential difference of each one of these capacitors. Okay, again, similar to what we had in the case of resistors. And so what we have here is that the potential difference of the battery is the sum of the potential difference of each one of these capacitors. Okay, so with these two pieces of information, we'll be able to find the equivalent capacitance, the capacitance that we can use to substitute all of them into a single one. And this single one will be drawing the same current for this battery. Okay, so what we want to find, what is the equivalent capacitance? Okay, given that we use the same battery. All right, so what do we have in this case? Well, let's start now from this equation here. Okay, what is the potential difference of the battery? The potential difference of the battery will be the Q divided by the equivalent capacitance. So this is, I'm thinking now about this circuit here. Okay, how about V1? What is V1? V1, using this equation, right? V1 is going to be Q, because we said Q is the same for all of the capacitors. So Q divided by C1. What is V2? Q, again, we said is the same Q everywhere, divided by C2. What is V3? Q divided by C3. So from that, now we see that the Q's are the same everywhere, and now we arrive at this equation. 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So again, be careful. We have a circuit where the capacitors are in series, And what is the equation that we get for the equivalent capacitance? This one, 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. Okay, so don't get confused, don't mess up uh, circuits in series with circuits in parallel for resistors and for capacitors. The equation that we get is the opposite in this case. Okay?